So for ionic compounds, the metal is going to transfer electrons to the nonmetal, and in the process of doing that, the metal becomes a cation. Remember, it's the electrons that are changing. The protons do not change. Number of protons stays the same, and so by moving electrons around, if you gain electrons, you become negative. If you lose electrons, you become positive. And then we have an attraction between the positive and the negative ions, and that results in an ionic compound. So in Lewis theory, we represent this by moving electron dots from the metal to the nonmetal, which I did in the last section ahead of time. So let's write the Lewis structures for potassium and chlorine and show what happens when they form an ionic compound. So potassium is K. And how many valence electrons does potassium have? It just has one. Chlorine is Cl, and how many valence electrons? 7. So there we have the Lewis structures for the atoms, potassium and chlorine. Potassium wants to get rid of that electron, and so it's going to transfer it to the chlorine. And so I'm going to erase this guy now because it moved over. So this now has a positive 1 charge, and this has a negative 1 charge. These minus signs have a way of getting lost in the dots sometimes, and so the convention is for these ions, the anions, we draw the Lewis structure, put brackets around the whole thing, all the dots, and we put the charge on the outside. We don't need to do that for the cations because there's no dots taking up spaces. Now, does this mean that potassium has no valence electrons now? No, it just means we peeled off that outer layer that wasn't complete, and underneath is a beautiful full layer. But in Lewis theory, we choose not to go ahead and draw those dots in because it gets confusing when you've got dots coming out of nowhere. So we just shift them around, and when we understand that if you get rid of all of somebody's valence electrons, that underneath it's full. And so we want to just be able to keep the same number of dots. We don't want dots appearing and disappearing. So however many dots you start with, that's how many you end up with. So what we ended up with there is the chloride ion has an octet. It's got 8 electrons around it, 8 dots. The potassium lost its only valence electron, and now it has an octet in the previous shell. When you take off the 3s electrons, now the 2 is the valence shell. So let's just, so potassium, I'm sorry, I was thinking of sodium. It's the 4. Do I have space to write all that there? I don't think I do. So potassium is 1s2, 2s2, 2p6, 3s2, I liked the magnesium example better, 3p6, 4s2. I'm sorry, 4s1. Good grief. That's the electron configuration for potassium. When we get rid of that 1 electron, that valence electron was in the 4th principal shell. Now that shell is empty. So now what is the valence shell? It's the 3rd. How many electrons are there? 8. 2 plus 6. So potassium, even though we draw him without any dots as a Lewis structure, he does have a full valence shell. He has an octet as an ion. With the anion, we usually put brackets and the charge in the upper right corner. This is very, very important right here. In mastering chemistry, you put the charges, but you don't do the brackets. Why? Because the program can't do brackets, okay? It can do lots and lots of things. It can't do the brackets. So please, do not text me and ask me how to put brackets on your Lewis structures, because I will tell you, you can't. If you look at the instructions, it does mention that there's no brackets. So you put the charge. When you're drawing it with your hand and a pencil, put the brackets. So let's write the Lewis structure for the compound sodium bromide. So I'm going to do a little extra work here, just for illustration. How many valence electrons does sodium have? 1. And how many does bromine have? 7. So sodium and bromine are going to see how they can help each other out. What's going to happen? The sodium's going to lose 1 and give it to the bromine. Right? And then what do we end up with? We end up with sodium with no valence electrons, and now it has a +1 charge. We end up with bromide, and this now has 8. It has an octet. And this has a charge, so I'm going to put it in brackets and put the charge on the outside. So this is the Lewis structure for the compound. We're just showing the 2 ions sitting next to each other. They're attracted to each other. This I just did to help you show why they do that, to help show you why they did that. Any questions? Lewis theory helps us predict chemical formulas. We learned how to predict these from the periodic table. We said, oh, well, barium is in group 2, it forms a +2. Fluorine's in group 7, it forms a -1. We do the crisscross charge thing, and we come up with this formula. But why? And what's the basis? Where did that come from? Did we make that up? No. Lewis theory explains, right? That's what a theory does. It explains why. It doesn't just say this is what happens. So let's look at why barium and fluorine do that. How many valence electrons does barium have? 2. And fluorine has 7. So what's going to happen here? The barium is going to give an electron to the fluorine. When that happens, the fluorine develops a negative charge because it has an extra electron. The barium now has a positive charge. Is the fluorine happy? The fluorine's tickled pink. It's got 8 octet. Awesome. Great. Good. We're done. Is the barium happy? No. Barium's like, well, I'm closer, but I still have this 1 electron. And electrons, you can't just like throw them away. You have to give them to someone. It's a little bit like a baby. You know, you're out in public, and what do you do with the baby? You can't just put them down on the floor in the middle of the mall, right? Not if you want to continue on with your life as normal. Bad things will happen if you do stuff like that. You hand the baby to someone else. You have to find someone who's willing to hold the baby for you. So barium is looking around for someone to take care of this electron for him. Well, if there's 1 fluorine around, there's probably another fluorine around, right? Here's another fluorine atom with 7 electrons. So barium's like, hey, you other fluorine over there. Let me give you this electron. And this fluorine's like, great, I was looking for one. So now this barium has a 2+ charge, and this fluorine has become fluoride with a -1 charge. And that is why we get 1 barium ion and 2 fluoride ions together, that ratio of 1 to 2. Because that's the way the electrons can transfer around and work out. Let's do another one. This one's fun. Okay, let's see if I can do it better than I did it in if I sell you? Magnesium and nitrogen. Magnesium has how many valence electrons? 2. And nitrogen has 5. No, I don't want to do that. 1, 2, 3, 4, 5. So what's going to happen here? The magnesium says, hey, you need some electrons. Here, take this one. It's like, okay, well, that's great. Now we got a +1 charge here and a -1 charge here. But neither of them's happy yet. So the magnesium says, you need another one. I need to get rid of this one. You need another one. Here, take this one too. So that one moves over there. Now magnesium has a 2+ charge, and nitrogen has a 2- charge. Is anybody happy yet? Magnesium's happy. Is the nitrogen happy? No. Well, if there's one magnesium ion, one magnesium atom, there's probably another one. So let's recruit another one. This one also has 2 valence electrons. And so this nitrogen says, hey, you, come over here. Share that electron with me. And the magnesium says, I'm not really into sharing. How about I just give it to you? Here, you just take it. I don't need it back. Now, nitrogen has a 3- charge, and this magnesium has a +1. Now, who's happy? The nitrogen. So we're going to put a bracket. He's happy. The first magnesium's happy, but now we've got this happier magnesium plus ion, but he's not entirely good. So call in another nitrogen. So this magnesium can put that give that electron to this nitrogen. Now this magnesium has a 2+ charge. That nitrogen has a -1 charge. The second magnesium is happy, but now we've got a nitrogen who's still not satisfied. And you may be thinking, this is going to go on forever, right? This is like your grandma with the bread and with it. Yeah, bread and jam all day long. No, it'll come out even eventually. Well, nitrogen needs electrons. We need another magnesium who's willing to get rid of electrons. So here's another magnesium atom with 2 valence electrons. So take 1 from the magnesium and give it to the nitrogen. Now we've got a 2- charge on the nitrogen and a +1 charge on the magnesium. Now take this other electron and give it to the nitrogen. Now this is a 2+, and this is a 3-. And we're done with him, so we're going to put brackets. And look, it finally came out even. But it took 3 magnesium ions and 2 nitrogen atoms to get together and have all those electrons work out. So the formula for this compound, we're just going to look at what we've drawn here. We've got, that's not what I wanted to do. We've got 1, 2, 3 magnesiums, so Mg3, and we have 2 nitrogens, so the formula is Mg3 and 2. Now, predicting that formula just by looking at charges that you get off the periodic table is faster, isn't it? But this explains why what we do from the periodic table works. It's because of the valence electrons and getting rid of them to form octets, those full valence shells. And that's what the reason behind this. Any questions?